At the northernmost point of mainland Europe, a lighthouse performed exactly as designed. Slettnes Lighthouse maintained its beacon schedule, transmitted regulation signals, and provided consistent visual reference points for Arctic shipping lanes. Maritime authorities documented proper maintenance cycles, verified signal strength, and confirmed operational compliance with international standards. Vessels approaching these waters received the navigation guidance that lighthouse technology was engineered to deliver. Yet within this framework of technical correctness, a systematic failure mechanism operated. The lighthouse's reliable presence established an expectation of navigational predictability in an environment where local conditions rendered such predictability impossible. Ice formation patterns, sudden visibility changes, and current variations occurred on timescales that exceeded the lighthouse capacity to communicate real-time hazard information. The navigation system functioned according to its design philosophy, providing fixed reference points for dead reckoning, while the operational environment demanded dynamic hazard assessment capabilities that this design philosophy could not accommodate. Ships approached Slettnes waters with confidence derived from lighthouse visibility, following established navigation protocols that assumed environmental conditions would remain within the parameters for which the lighthouse system was optimized. The vessels were guided by instruments that reported accurately, while failing to convey the information structure necessary for survival in rapidly changing Arctic conditions. How can navigation infrastructure designed for safety systematically increase the probability of maritime disaster? Slettnes Lighthouse emerged from the convergence of two early 20th century engineering imperatives: the expansion of Arctic shipping routes and the application of standardized lighthouse technology to previously uncharted waters. Completed in 1905, the facility represented state-of-the-art lighthouse engineering, featuring a cast-iron tower structure and reinforced living quarters specifically designed to withstand Arctic storms. The lighthouse's positioning at 71°05 feet and 20°8'12 feet placed it at the threshold of the Barents Sea, where it would serve as the primary navigational reference for vessels transiting between the North Atlantic and Arctic shipping lanes. The design specifications reflected established lighthouse engineering principles developed for temperate maritime environments. The optical system employed a standardized Fresnel lens configuration capable of projecting a visible signal across distances calculated according to standard atmospheric visibility models. These calculations assumed atmospheric conditions consistent with lower-latitude maritime operations, where visibility patterns followed predictable seasonal and weather-related variations. The lighthouse's signal intensity and timing sequences conformed to international maritime navigation standards that had proven effective in established shipping corridors. However, the fundamental design assumption underlying all lighthouse technology, that environmental conditions would remain sufficiently stable to permit reliable signal-to-navigation correlation, faced systematic violation in Arctic waters. The lighthouse engineering philosophy presumed that atmospheric visibility, when present, would provide sufficient optical transmission for navigation decision-making. This assumption proved systematically false in Arctic conditions, where atmospheric optical properties underwent rapid and unpredictable transformations that rendered lighthouse signals simultaneously visible and navigationally misleading. Arctic atmospheric physics introduced systematic distortions to lighthouse signal interpretation that standard lighthouse design could not accommodate. Ice crystal formations in the atmosphere created optical refraction patterns that displaced apparent lighthouse position relative to actual position, particularly during conditions of atmospheric stability that increased signal visibility range. Temperature inversion layers, common in Arctic atmospheric conditions, bent lighthouse signals in ways that made the light source appear to originate from positions significantly different from the actual lighthouse location. These phenomena occurred most frequently during periods when atmospheric clarity made lighthouse signals most visible and apparently most reliable. The lighthouse's position at the interface between open ocean and coastal waters created additional systematic complications for navigation safety. While the lighthouse itself remained on stable ground, the maritime environment it was designed to illuminate underwent continuous transformation through ice formation, current shifts, and seasonal variations that altered the fundamental geography of navigable waters. Standard lighthouse engineering assumed that the relationship between lighthouse position and safe navigation corridors would remain constant, with variations occurring slowly enough to permit chart updates and mariner notification. Arctic conditions systematically violated this assumption. Ice formation patterns around Slettnes created navigation channels that appeared and disappeared within hours, while current variations shifted the location of safe approach corridors on timescales far shorter than the lighthouse's capacity to communicate such changes. The lighthouse continued to mark a fixed geographical position, while the navigable waterways it was intended to illuminate underwent continuous and unpredictable reconfiguration. The optical design philosophy embedded in lighthouse technology assumed that visibility of the signal correlated positively with navigation safety, that mariners could rely on lighthouse signal strength and clarity as indicators of suitable navigation conditions. This assumption proved systematically dangerous in Arctic waters, where lighthouse signals often achieved maximum visibility during atmospheric conditions that coincided with the most rapid ice formation and current pattern changes. Clear Arctic atmospheric conditions, which enhanced lighthouse signal transmission, frequently accompanied temperature patterns that accelerated ice formation in navigation channels. Furthermore, the lighthouse's design prioritized signal consistency and reliability, characteristics that became systematically misleading in an environment requiring dynamic hazard communication. The lighthouse mechanism that ensured consistent signal timing and intensity, qualities essential for navigation in stable maritime environments, prevented the communication of real-time environmental variability that determined navigation safety in Arctic waters. The lighthouse's reliability became its fundamental limitation, providing consistent information about fixed geographical position while remaining systematically unable to communicate the dynamic environmental conditions that determined whether approach to that position was safe or lethal. The engineering documentation for Slettnes Lighthouse reflected design optimization for signal projection and mechanical reliability under extreme weather conditions, but revealed no consideration of the fundamental mismatch between fixed position navigation aids and the dynamic hazard environment they were intended to serve. The lighthouse's cast iron construction and reinforced mechanical systems demonstrated engineering solutions for maintaining signal consistency under harsh physical conditions, while the navigation safety problem required information systems capable of communicating environmental variability rather than technological consistency. Maritime navigation protocols developed for lighthouse-assisted navigation assumed that environmental hazards would be detectable through direct observation coordinated with lighthouse position reference. These protocols proved systematically inadequate in Arctic conditions, where ice formation occurred below the waterline and remained invisible until vessels encountered physical contact, while atmospheric conditions that provided excellent lighthouse visibility simultaneously obscured surface ice patterns that determine navigation safety. The systematic nature of navigation failures around Slettnes reflected the fundamental incompatibility between lighthouse design assumptions and Arctic maritime environmental characteristics. Lighthouse engineering had evolved to solve navigation problems in environments where hazards remained relatively static and where signal visibility correlated with navigation safety. Arctic conditions inverted these relationships, creating environments where lighthouse signal clarity often coincided with maximum hazard development and where the static nature of lighthouse signals prevented communication of the dynamic information necessary for survival. The lighthouse operated according to design specifications while failing to provide the environmental safety information that mariners required for Arctic navigation. This created systematic false confidence in technological navigation solutions while exposing vessels to environmental hazards that lighthouse-based navigation could not detect or communicate. The failure emerged not from lighthouse malfunction or operator error, but from the systematic application of navigation technology to environmental conditions that violated the fundamental assumptions underlying lighthouse design philosophy. The systematic navigation failures around Slettnes emerged from institutional frameworks that had evolved to optimize lighthouse-based navigation while systematically discouraging the environmental hazard assessment capabilities required for Arctic maritime safety. Maritime training curricula, regulatory protocols, and economic incentive structures combined to create systematic over-reliance on technological navigation aids precisely in conditions where such reliance proved most dangerous. Standard maritime navigation training protocols reflected decades of successful lighthouse-assisted navigation in temperate waters, where lighthouse reliability correlated positively with navigation safety. Training programs emphasized lighthouse signal recognition, bearing calculation, and position-fixing techniques that assumed environmental conditions would remain sufficiently stable to permit accurate dead reckoning between known lighthouse positions. These protocols had proven effective in established shipping corridors where environmental hazards developed slowly enough to permit detection and avoidance through traditional navigation techniques. However, the training framework that prepared mariners for lighthouse-assisted navigation systematically underemphasized the environmental assessment capabilities required for safe Arctic navigation. Navigation curricula focused on technical procedures for lighthouse signal interpretation while providing minimal instruction in rapid environmental hazard recognition. Mariners learned to calculate precise bearings from lighthouse signals, but received limited training in detecting the ice formation patterns, current variations, and visibility changes that determine navigation safety in Arctic waters. The institutional emphasis on lighthouse-based navigation reflected broader maritime industry preferences for technological solutions over environmental expertise. Lighthouse navigation provided quantifiable, standardized procedures that could be documented, regulated, and verified through established maritime certification processes. Environmental hazard assessment, by contrast, required experiential knowledge and judgment capabilities that proved difficult to standardize or certify through conventional maritime training systems. This institutional bias toward technological solutions created systematic gaps in mariner preparation for Arctic conditions. Navigation training emphasized the mechanical aspects of lighthouse-assisted navigation, signal recognition, bearing calculation, and chart work, while systematically de-emphasizing the environmental observation skills necessary for detecting rapid hazard development. Mariners approaching Arctic waters possessed sophisticated technical knowledge of lighthouse navigation procedures, but lacked the environmental assessment capabilities required to recognize when lighthouse guidance had become systematically misleading. The regulatory framework governing Arctic maritime operations reinforced this technological over-reliance through standards that emphasized lighthouse availability and signal reliability while providing minimal requirements for environmental hazard assessment capabilities. Maritime regulations specified minimum lighthouse signal ranges, required lighthouse maintenance schedules, and established protocols for lighthouse-assisted navigation, but failed to address the fundamental limitation of lighthouse technology in rapidly changing environmental conditions. Lighthouse keeper training and operational protocols reflected similar systematic limitations. Lighthouse keepers at Slettnes received extensive training in equipment maintenance, signal timing, and weather reporting, but their role definition focused on maintaining technological reliability rather than providing real-time environmental hazard assessment. The keeper's primary responsibility involved ensuring lighthouse signal consistency, not communicating the dynamic environmental conditions that determine navigation safety for approaching vessels. Weather reporting systems available to lighthouse keepers proved systematically inadequate for Arctic navigation safety requirements. Standard meteorological reporting focused on atmospheric conditions, temperature, wind speed, visibility, while providing limited capability for communicating the ice formation patterns, current variations, and rapid environmental changes that created navigation hazards. Lighthouse keepers could report that weather conditions were clear, and lighthouse signals were functioning properly, while remaining systematically unable to communicate that ice formation had created navigation traps in approach channels. Communication protocols between lighthouse operations and shipping traffic reflected the systematic institutional preference for technological rather than environmental information. Standard maritime communication procedures emphasized lighthouse signal status, bearing information, and position reports while providing minimal framework for communicating environmental hazard assessments. Ships approaching Slettnes received technical information about lighthouse functionality but lacked systematic access to real-time environmental hazard intelligence. Economic incentive structures within the maritime industry systematically reinforced lighthouse-based navigation over-reliance while discouraging the conservative navigation practices required for Arctic safety. Shipping schedules and cost structures favored predictable transit times that could be calculated using lighthouse-based dead reckoning techniques. Environmental hazard assessment, which might require route modifications, schedule delays, or increased safety margins, imposed economic costs that shipping operators had systematic incentives to minimize. The development of Arctic shipping routes created particular pressure for technological navigation solutions that could provide the predictability required for commercial operations. Lighthouse infrastructure promised to extend established navigation techniques into Arctic waters, enabling commercial shipping operations to calculate transit times, fuel requirements, and scheduling with the reliability that temperate water lighthouse navigation had historically provided. This economic pressure systematically discouraged recognition that Arctic environmental conditions might require fundamentally different navigation approaches. Insurance and regulatory frameworks reinforced these economic incentives by establishing liability and certification requirements based on lighthouse-assisted navigation compliance rather than environmental hazard assessment capabilities. Maritime insurance policies and regulatory certifications emphasized adherence to established lighthouse navigation procedures while providing limited recognition or incentive for environmental assessment capabilities that might improve navigation safety in Arctic conditions. The institutional framework governing lighthouse operations created additional systematic limitations. Lighthouse facilities operated according to standardized procedures developed for temperate maritime environments, where consistent signal projection provided adequate navigation safety information. These procedures emphasized technological reliability, ensuring lighthouse signals operated according to specification, while systematically limiting lighthouse operators' capability to communicate environmental hazard information that fell outside standard technological parameters. Lighthouse keeper training reflected these institutional limitations. Keepers learned to maintain equipment, monitor signal consistency, and report technical malfunctions, but received minimal preparation for assessing or communicating environmental hazards that might render lighthouse guidance systematically dangerous. The institutional role definition for lighthouse keepers emphasized technological reliability rather than environmental safety assessment, creating systematic gaps in hazard communication capability. Maritime education institutions reinforced lighthouse navigation over reliance through curricula that emphasized technological competency while systematically underweighting environmental expertise. Navigation programs focused on lighthouse signal interpretation, chart work, and position calculation, while providing minimal instruction in the environmental observation skills required for Arctic navigation safety. Graduates entered Arctic waters with sophisticated lighthouse navigation capabilities, but lacking the environmental assessment expertise necessary to recognize when technological navigation had become systematically dangerous. Professional advancement within maritime careers further reinforced technological navigation preferences. Career progression favored demonstrated competency in established navigation procedures rather than environmental assessment capabilities that proved difficult to standardize or certify. Mariners had systematic incentives to develop lighthouse navigation expertise, while lacking comparable incentives to develop the environmental hazard recognition skills required for Arctic navigation safety. The systematic institutional preference for technological solutions over environmental expertise created cumulative effects that amplified navigation safety risks in Arctic conditions. Each component of the maritime system, training, regulation, economic incentives, professional advancement, independently favored lighthouse-based navigation while discouraging environmental hazard assessment. These individual institutional biases combined to create systematic over-reliance on technological navigation precisely in conditions where such reliance proved most dangerous. Furthermore, the institutional framework provided no systematic mechanism for recognizing or correcting this over-reliance. Safety assessment procedures focused on technological compliance rather than environmental hazard recognition, making it systematically difficult to identify cases where lighthouse guidance had become misleading. Incident investigation protocols emphasized equipment malfunction or procedural violations while providing limited framework for analyzing cases where technological navigation had functioned according to specification while creating systematic safety hazards. The isolation and harsh conditions at Slettnes exacerbated these institutional limitations. Lighthouse keepers faced months of isolation, limited communication with outside authorities, and extreme weather conditions that made environmental observation difficult and hazardous. Under these conditions, institutional pressure to maintain lighthouse signal consistency took precedence over environmental hazard assessment capabilities that proved difficult to maintain under extreme operational conditions. Communication limitations further amplified institutional biases toward technological solutions. Arctic communication systems provided reliable capability for transmitting standardized lighthouse signal information, but lacked capacity for communicating complex environmental hazard assessments. This technical limitation reinforced institutional preferences for technological navigation information, while systematically limiting environmental hazard communication capability. The convergence of these institutional factors created systematic preparation gaps that made lighthouse navigation failures inevitable rather than accidental. Mariners approaching Slettnes possessed the technological navigation capabilities that institutional frameworks had trained them to develop while systematically lacking the environmental assessment expertise required for Arctic navigation safety. The institutional system had optimized itself for lighthouse-based navigation success while creating systematic inability to recognize. The systematic failure of lighthouse navigation at Slettnes manifested most clearly during specific incident sequences where lighthouse signals remained fully functional while environmental conditions underwent rapid transformations that rendered lighthouse-guided navigation systematically dangerous. These incidents revealed the fundamental disconnect between lighthouse signal reliability and navigation safety, demonstrating how technological functionality could persist while creating systematic navigation traps. During the early winter months when Arctic shipping remained active, atmospheric conditions around Slettnes frequently created optimal lighthouse signal visibility coinciding with rapid ice formation that transformed navigation channels within hours. The lighthouse's powerful Fresnel lens system achieved maximum signal projection range during clear, cold atmospheric conditions that simultaneously accelerated ice crystal formation and coastal ice development. This created systematic scenarios where lighthouse signals provided excellent visibility and apparent navigation reliability, while ice formation eliminated safe approach corridors. The documented incident pattern showed lighthouse signals maintaining full intensity and timing consistency, while ice formation created navigation hazards that remained invisible to lighthouse-assisted navigation techniques. Ships approaching Slettnes during periods of excellent lighthouse visibility encountered ice formations that had developed between their last position fix and their approach to lighthouse-guided navigation corridors. The lighthouse continued to mark its geographical position accurately, while the maritime environment around that position underwent transformation that eliminated previously safe navigation routes. Atmospheric physics around Slettnes created particularly systematic problems for lighthouse-assisted navigation during Arctic atmospheric inversion conditions. Temperature inversion layers, which increased lighthouse signal visibility range by reducing atmospheric dispersion, simultaneously created optical refraction effects that displaced apparent lighthouse position relative to actual geographical location. Ships using lighthouse bearings for navigation calculations during these conditions received systematically inaccurate position information precisely when lighthouse signals appeared most reliable and visible. These atmospheric inversion conditions occurred most frequently during weather patterns that also accelerated ice formation and current pattern changes around Slettnes. The same meteorological conditions that enhanced lighthouse signal transmission also created rapid environmental changes that invalidated the navigation safety assumptions underlying lighthouse-assisted approach procedures. Ships experienced maximum lighthouse signal clarity during conditions that created maximum navigation hazard development. Current pattern analysis around Slettnes revealed systematic variations that occurred on timescales shorter than lighthouse-assisted navigation response capability. Tidal interactions with ice formation and seasonal current shifts created navigation channel configurations that changed within hours, while lighthouse-based dead reckoning techniques assumed navigation corridor stability over periods of days or weeks. Ships approaching using lighthouse-guided navigation calculations based their route planning on environmental assumptions that no longer corresponded to actual navigation channel configuration. The lighthouse signal itself provided no mechanism for communicating these rapid environmental changes. The optical system designed for signal consistency and reliability continued to project the same timing sequences and intensity patterns regardless of environmental condition variations around the lighthouse. Ships received technically accurate lighthouse signals while lacking any systematic indication that the environmental context for lighthouse-assisted navigation had fundamentally changed since their last position calculation. Ice formation patterns around Slettnes created particularly systematic navigation traps during periods of excellent lighthouse visibility. Surface ice development that remained invisible from lighthouse-guided approach distances created navigation channels that appeared clear while containing ice formations sufficient to trap or damage vessels. The lighthouse signal provided accurate geographical reference while offering no indication that approach corridors had become impassable. Furthermore, ice formation below the waterline created systematic hazards that lighthouse signals could not communicate. Underwater ice projections and shifting ice formations created obstacles that remained invisible to visual navigation techniques while creating systematic damage potential for vessels following lighthouse-guided approach routes. Ships using lighthouse bearings for navigation received accurate position information while remaining systematically unaware of underwater hazard development. The communication systems available at Slettnes proved systematically inadequate for providing real-time environmental hazard information that might supplement lighthouse signal navigation. Radio communication protocols focused on lighthouse signal status and weather observations rather than dynamic navigation hazard assessment. Lighthouse keepers could report excellent signal visibility in clear weather conditions while lacking systematic capability to communicate ice formation patterns or current variations that affected navigation safety. Weather reporting protocols emphasized atmospheric conditions rather than maritime navigation hazards. Standard meteorological observations recorded temperature, wind speed, and visibility data that confirmed excellent lighthouse signal projection conditions while providing minimal information about ice formation, current patterns, or navigation channel configuration changes that determined approach safety. Ships received weather reports confirming excellent lighthouse visibility, while lacking systematic information about environmental changes that made lighthouse-guided navigation dangerous. The timing of these environmental changes created additional systematic problems for lighthouse-assisted navigation. Ice formation and current pattern shifts occurred most rapidly during the clear, calm conditions that provided optimal lighthouse signal visibility. Ships approaching during periods of maximum lighthouse signal reliability encountered maximum rates of environmental change that invalidated lighthouse-guided navigation assumptions. Navigation decision-making timelines proved systematically incompatible with environmental change rates around Slettnes. Standard lighthouse-assisted navigation procedures assumed environmental stability sufficient to permit approach route planning based on lighthouse bearings calculated hours or days before final approach. Arctic environmental conditions created change rates that invalidated these assumptions within hours, while ships committed to lighthouse-guided approaches lacked systematic capability to detect or respond to rapid environmental changes. The systematic nature of these failures reflected fundamental incompatibilities between lighthouse navigation assumptions and Arctic environmental characteristics, rather than exceptional or unpredictable conditions. Ice formation patterns, current variations, and atmospheric effects occurred according to predictable physical processes, but these processes operated on timescales and spatial scales that lighthouse navigation systems could not accommodate. Lighthouse signal documentation showed consistent functionality throughout periods when environmental conditions rendered lighthouse guidance systematically dangerous. Equipment logs recorded proper signal timing, intensity maintenance, and mechanical reliability during incidents when lighthouse-guided navigation resulted in vessel groundings, ice entrapment, or navigation hazard encounters. the lighthouse performed according to design specifications, while the environmental context for lighthouse navigation underwent changes that made technological functionality systematically misleading. Position calculation errors during atmospheric inversion conditions created additional systematic navigation hazards. Ships using lighthouse bearings during temperature inversion events calculated positions that differed from actual position by distances sufficient to place vessels in navigation hazard zones, while appearing to confirm safe approach corridor navigation. The lighthouse signal provided technically accurate information that atmospheric conditions transformed into systematically inaccurate navigation guidance. These systematic position calculation errors occurred most frequently during conditions that enhanced lighthouse signal clarity and apparent reliability. Ships received lighthouse signals with exceptional visibility and stability, while atmospheric physics systematically distorted the navigation information derived from those signals. The enhanced signal quality created false confidence in navigation accuracy, precisely when atmospheric conditions made lighthouse-based position calculation most unreliable. The documentation of multiple incidents following similar patterns revealed the systematic rather than accidental nature of lighthouse navigation failures around Slettnes. Ships approaching during different seasons, weather conditions, and times encountered systematically similar problems. Lighthouse signals remained functional, while environmental conditions rendered lighthouse guidance dangerous. This pattern consistency demonstrated fundamental incompatibilities between lighthouse technology and Arctic navigation requirements, rather than exceptional circumstances or equipment failures. Communication delays between environmental observation and navigation decision implementation created additional systematic hazards. Even when lighthouse keepers or other observers detected rapid environmental changes, communication systems proved inadequate for providing real-time hazard warnings to approaching vessels. Ships committed to lighthouse-guided approaches continued following navigation plans based on outdated environmental assumptions, while lacking systematic capability to receive updated hazard information. The physical geography around Slettnes amplified these communication limitations. The lighthouse's position at the northern extremity of mainland Europe created communication shadow zones where radio signals experienced interference or complete blockage. Ships approaching from certain directions lost communication capability precisely when they most required real-time environmental hazard information to supplement lighthouse-guided navigation. Navigation equipment available to vessels approaching Slettnes proved systematically inadequate for detecting the environmental changes that invalidated lighthouse navigation assumptions. Standard maritime navigation instruments provided accurate lighthouse bearing calculation and position fixing capabilities while offering minimal capacity for ice formation detection, underwater obstacle identification, or current pattern assessment. Ships possessed sophisticated lighthouse navigation capabilities while lacking the environmental assessment instruments required for Arctic navigation safety. The convergence of these factors created systematic navigation traps where lighthouse functionality persisted while navigation safety deteriorated. Ships approached Slettnes using established lighthouse navigation procedures that had proven successful in temperate waters, encountering environmental conditions that violated the fundamental assumptions underlying those procedures. The lighthouse continued to mark its geographical position accurately, while the environmental context for safe navigation to that position underwent rapid and systematic transformation. These incidents demonstrated the critical distinction between lighthouse signal functionality and navigation safety. Lighthouse signals could maintain technical performance specifications, while the navigation information derived from those signals became systematically dangerous. The lighthouse provided consistent geographical reference, while environmental conditions eliminated the safe navigation corridors that lighthouse-guided approaches assumed would remain accessible. The systematic repetition of these incident patterns across different vessels, seasons, and environmental conditions revealed that lighthouse navigation failures around Slettnes reflected fundamental technological limitations rather than exceptional circumstances or operational errors. The lighthouse navigation system proved systematically inadequate for Arctic conditions, not because of equipment malfunction or procedural violations, but because Arctic environmental characteristics violated the basic assumptions underlying lighthouse navigation design philosophy. The physical mechanisms underlying lighthouse navigation failures around Slettnes operated according to predictable thermodynamic and oceanographic processes that created systematic navigation traps precisely when lighthouse signals provided optimal visibility and apparent reliability. Ice formation physics, current pattern dynamics, and coastal bathymetry combined to produce environmental conditions that systematically invalidated lighthouse navigation assumptions while remaining largely invisible to lighthouse-assisted navigation techniques. Arctic ice formation around Slettnes followed thermodynamic principles that created navigation hazards on timescales far shorter than lighthouse-based navigation response capabilities. Sea ice formation initiated when surface water temperatures dropped below the freezing point of seawater, approximately -1.8 degrees Celsius. But the formation process accelerated exponentially under specific atmospheric and oceanographic conditions that occurred most frequently during periods of excellent lighthouse visibility. The thermodynamic processes governing ice formation created systematic timing conflicts with lighthouse navigation procedures. Initial ice crystal formation occurred within hours of appropriate temperature conditions, while significant ice accumulations sufficient to obstruct navigation developed within 6 to 12 hours under optimal formation conditions. These formation timescales proved systematically incompatible with lighthouse-assisted navigation planning, which assumed environmental stability over periods of 24 to 48 hours for approach route calculation and execution. Atmospheric temperature patterns around Slettnes created particularly systematic ice formation acceleration during clear, calm conditions that enhanced lighthouse signal transmission. Radiational cooling under clear skies rapidly reduced surface water temperatures below ice formation thresholds, while calm atmospheric conditions prevented wind mixing that might delay ice formation by maintaining surface water circulation. The meteorological conditions that provided optimal lighthouse visibility systematically accelerated ice formation processes. Wind pattern analysis revealed additional systematic relationships between lighthouse signal clarity and navigation hazard development. Offshore wind patterns that cleared atmospheric obscuration and enhanced lighthouse visibility simultaneously created surface water circulation patterns that concentrated ice formation in coastal approaches where lighthouse-guided navigation routes converged. Ships approaching during periods of maximum lighthouse signal clarity encountered ice concentrations in precisely the navigation corridors that lighthouse guidance directed them to follow. The physical oceanography around Slettnes created systematic ice formation patterns that lighthouse navigation could not detect or communicate. Coastal bathymetry created shallow water zones where ice formation occurred earlier and more rapidly than in deeper approach channels, while tidal circulation patterns concentrated ice formation in specific geographical areas that coincided with lighthouse-guided approach routes. These bathymetric and tidal effects created predictable ice formation patterns that lighthouse signals could not communicate to approaching vessels. Current pattern analysis demonstrated systematic relationships between lighthouse visibility conditions and navigation channel obstruction. Tidal currents around Slettnes created circulation patterns that varied with seasonal, lunar, and atmospheric pressure cycles, shifting the location of safe navigation channels on timescales far shorter than lighthouse navigation planning assumed. During periods of excellent lighthouse visibility, current patterns frequently created ice accumulation zones that blocked previously safe approach corridors while opening apparently clear channels that contained underwater ice formations. The interaction between surface ice formation and subsurface ice development created additional, systematic navigation hazards that lighthouse signals could not communicate. While surface ice formation provided some visual indication of ice presence, underwater ice formation and ice shelf development occurred without surface manifestation until ice thickness reached critical levels. Ships approaching using lighthouse guidance encountered underwater ice obstacles that remained invisible to visual navigation techniques while creating systematic grounding or hull damage potential. Ice formation physics created systematic false navigation corridors that appeared clear from lighthouse observation distances while containing ice concentrations sufficient to trap or damage vessels. Surface ice formation patterns frequently created apparent channels through ice fields, but these channels often terminated in ice accumulations or led to shallow water areas where ice formation had created navigation obstacles. Lighthouse signals provided accurate geographical reference to these apparent channels while offering no indication that the channels led to systematic navigation traps. The physical properties of newly formed ice created additional systematic problems for lighthouse-assisted navigation. Fresh ice formation often appeared as dark water from distances compatible with lighthouse navigation range, while possessing sufficient density and thickness to obstruct vessel passage. Ships using lighthouse-guided navigation received visual confirmation of apparently clear water while approaching ice formations that could prevent passage or create hull damage. Vessel physics during ice contact revealed systematic damage patterns that reflected fundamental incompatibilities between lighthouse navigation assumptions and Arctic environmental conditions. Ships designed for temperate water navigation possessed hull configurations optimized for open water performance rather than ice contact resistance. When lighthouse-guided navigation led these vessels into ice formations, hull design characteristics created systematic vulnerability to ice damage that could compromise vessel integrity and navigation capability. The momentum and inertia characteristics of vessels following lighthouse-guided approaches created additional systematic hazards during ice encounters. Ships calculating approach speeds based on lighthouse bearing changes and estimated arrival times often maintained velocities incompatible with safe ice navigation. When these vessels encountered ice formations, their momentum characteristics prevented rapid course corrections or emergency stops, leading to systematic ice impact scenarios that could cause hull damage, rudder damage, or complete vessel entrapment. Steering response characteristics during ice contact created systematic loss of navigation control that amplified the consequences of lighthouse navigation failures. Ice contact along vessel hulls created asymmetric drag forces that overwhelmed steering system capabilities, particularly for vessels not specifically designed for ice navigation. Ships entering ice fields while following lighthouse-guided routes experienced systematic steering system failure that prevented course corrections and led to deeper ice entrapment. Engine cooling system vulnerability during ice navigation created additional systematic failure modes for vessels following lighthouse guidance into ice-affected waters. Ice formation around engine water intake systems could restrict cooling water flow, leading to engine overheating and power loss precisely when vessels required maximum maneuverability for ice navigation. Ships following lighthouse-guided approaches into ice conditions experienced systematic propulsion system failure that eliminated their capability to escape ice entrapment. The physical geography around Slettnes created systematic current and ice interaction patterns that amplified navigation hazards during periods of optimal lighthouse visibility. Coastal topography channeled tidal flows and wind-driven currents into specific geographical areas, creating systematic ice accumulation zones that coincided with lighthouse-guided approach routes. These geographical effects created predictable ice concentration patterns that lighthouse navigation could not communicate, but that systematically affected navigation safety. Bathymetric charts of Slettnes approaches revealed systematic shallow water zones where ice formation occurred earlier and persisted longer than lighthouse navigation planning assumed. These shallow areas created systematic grounding hazards for vessels following lighthouse-guided routes during ice formation periods, while remaining largely invisible to lighthouse-assisted navigation techniques. Ships using lighthouse bearings for navigation calculations often found themselves in shallow water areas where ice formation had created navigation obstacles and grounding potential. Tidal range analysis around Slettnes demonstrated systematic water level variations that affected ice formation patterns and navigation channel configuration on timescales incompatible with lighthouse navigation planning. Low tide conditions exposed additional shallow water areas and concentrated ice formation and navigation channels, while high tide conditions could temporarily clear ice accumulations that reformed during subsequent tidal cycles. These tidal effects created systematic variations in navigation channel safety that lighthouse signals could not communicate. The optical physics of lighthouse signals created systematic limitations for ice hazard detection that became critical during ice formation periods. Lighthouse signal characteristics, optimized for maximum transmission range, proved inadequate for illuminating surface ice formations that required specific lighting angles and intensities for visibility. Ships using lighthouse signals for navigation guidance lacked the optical information necessary to detect ice formations until direct visual contact occurred at distances too short for effective course correction. Atmospheric optical effects during Arctic conditions created additional systematic problems for lighthouse-assisted ice hazard detection. Temperature inversion layers that enhanced lighthouse signal visibility simultaneously created optical distortion effects that masked surface ice formations, or displaced their apparent positions relative to actual ice locations. Ships receiving clear lighthouse signals often encountered ice formations at positions different from where visual observation suggested ice presence, eliminating the possibility for effective avoidance maneuvers. The systematic nature of these physical processes created cumulative failure cascades, where individual environmental factors combined to create navigation hazard scenarios far more dangerous than lighthouse navigation planning anticipated. Ice formation acceleration during clear atmospheric conditions combined with current pattern changes, tidal variations, and optical limitation effects to create systematic navigation traps that proved impossible to avoid using lighthouse-assisted navigation techniques. Furthermore, the physical processes governing ice formation and current patterns around Slettnes operated according to seasonal and meteorological cycles that created systematic temporal patterns in navigation hazard development. Specific seasonal periods, lunar cycles, and weather patterns created predictably dangerous conditions for lighthouse navigation, but lighthouse signals provided no systematic mechanism for communicating these temporal hazard patterns to approaching vessels. The interaction between vessel design characteristics and Arctic environmental conditions created additional systematic failure modes that lighthouse navigation could neither predict nor prevent. Vessels designed for temperate water navigation possessed structural, mechanical, and operational characteristics that proved systematically inadequate for ice navigation conditions, while lighthouse-guided navigation approaches provided no systematic indication of environmental conditions that exceeded vessel design limitations. Temperature effects on vessel systems created systematic operational limitations during ice navigation that lighthouse planning could not accommodate. Cold atmospheric conditions affected engine performance, hydraulic system operation, and navigation equipment functionality in ways that reduced vessel maneuverability and navigation accuracy precisely when ice conditions required maximum operational capability. Ships following lighthouse-guided approaches into Arctic conditions experienced systematic operational degradation that amplified navigation hazard exposure. The documentation of vessel grounding incidents around Slettnes revealed systematic patterns where lighthouse navigation guidance led vessels into shallow water areas during ice formation periods. These grounding incidents occurred most frequently during conditions of excellent lighthouse visibility, when atmospheric and ice formation conditions created optimal lighthouse signal transmission, while simultaneously creating rapid ice development in navigation channels. Analysis of vessel damage patterns during ice encounters revealed systematic structural failure modes that reflected fundamental incompatibilities between temperate water vessel design and Arctic navigation requirements. Hull plating configurations, rudder mounting systems, and propeller design characteristics optimized for open water performance created systematic vulnerability to ice damage that could compromise vessel safety and navigation capability. The systematic repetition of these physical failure mechanisms across multiple vessels, seasons, and environmental conditions demonstrated that lighthouse navigation failures around Slettnes reflected fundamental physical incompatibilities rather than exceptional circumstances or operational errors. The physical processes governing Arctic environmental conditions operated according to predictable laws that systematically violated the assumptions. The systematic navigation failures around Slettnes created secondary crisis scenarios where rescue and stabilization attempts, constrained by the same lighthouse navigation frameworks that had created initial failures, often amplified rather than resolved emergency situations. Rescue operations designed for temperate maritime conditions proved systematically inadequate for Arctic emergencies where environmental conditions continued to evolve during rescue attempts, while communication and coordination systems optimized for lighthouse-assisted navigation created additional systematic hazards. Rescue operation protocols developed for maritime emergencies assumed environmental stability sufficient to permit rescue vessel navigation using established lighthouse-assisted techniques. These protocols proved systematically inadequate in Arctic conditions where environmental changes continued during rescue operations, often at accelerated rates due to weather patterns and ice formation processes that rescue activities themselves could not control or predict. When vessels became ice-trapped or grounded following lighthouse-guided approaches to Slettnes, rescue operations faced the same systematic navigation challenges that had created the original emergency. Rescue vessels approaching using lighthouse navigation encountered identical ice formation patterns, current variations, and atmospheric, optical effects that had trapped or grounded the original vessels. This created systematic scenarios where rescue attempts generated additional emergencies rather than resolving existing crises. The communication systems available for coordinating rescue operations around Slettnes proved systematically inadequate for managing dynamic emergency situations in rapidly changing environmental conditions. Radio communication protocols designed for lighthouse-assisted navigation emphasized position reporting and lighthouse-bearing information while providing minimal capability for communicating real-time environmental hazard assessments necessary for effective rescue coordination. Lighthouse keeper involvement in rescue coordination created additional systematic limitations. Lighthouse keepers possessed detailed knowledge of lighthouse signal characteristics and standard navigation procedures, but lacked systematic training or capability for environmental hazard assessment during emergency conditions. Keepers could provide accurate lighthouse signal information and weather observations while remaining systematically unable to communicate ice formation patterns, current variations, or environmental change rates that affected rescue operation safety. Rescue vessel navigation capabilities reflected the same technological over-reliance that had created initial navigation failures. Rescue craft designed for temperate water operations possessed lighthouse navigation equipment optimized for stable environmental conditions, while lacking the environmental assessment capabilities required for dynamic Arctic rescue operations. These vessels approached emergency situations using lighthouse-guided navigation techniques that exposed rescue operations to the same systematic hazards that had created the original emergencies. The timing constraints inherent in rescue operations created additional systematic complications for lighthouse-assisted navigation in Arctic conditions. Emergency response protocols emphasized rapid rescue vessel dispatch and arrival, but these timing requirements proved incompatible with the environmental assessment capabilities necessary for safe Arctic navigation. Rescue operations faced systematic conflicts between emergency response speed requirements and the environmental caution necessary for avoiding additional navigation failures. Weather deterioration during rescue operations created systematic amplification of navigation hazards that lighthouse-based rescue coordination could not accommodate. Arctic weather patterns frequently deteriorated rapidly during rescue operations, creating ice formation acceleration, visibility reduction, and current pattern changes that invalidated lighthouse navigation assumptions. Rescue operations initiated during acceptable lighthouse visibility conditions often encountered systematic weather deterioration that eliminated safe navigation options while rescue operations remained in progress. Ice formation acceleration during rescue operations created additional systematic hazards that lighthouse navigation could neither predict nor communicate. The mechanical disturbance created by vessel rescue attempts often accelerated local ice formation processes, while extended rescue operation duration provided additional time for ice accumulation that could trap rescue vessels alongside original emergency vessels. Lighthouse signals continued to provide geographical reference, while environmental conditions around rescue operations underwent systematic deterioration. Rescue equipment and techniques designed for temperate water operations proved systematically inadequate for Arctic rescue conditions. Standard maritime rescue equipment assumed open water conditions and mild weather environments, while Arctic rescue operations required specialized equipment for ice navigation, cold weather operation, and extended rescue duration in harsh environmental conditions. Rescue operations guided by lighthouse navigation often discovered equipment inadequacy only after committing to rescue approaches that could not be safely abandoned. Communication delays between rescue coordination centers and vessels operating in Slettnes waters created additional systematic hazards during emergency operations. Arctic communication systems experienced systematic interference and signal degradation during weather conditions that also accelerated navigation hazard development. Rescue operations lost communication capability precisely when environmental conditions required maximum coordination and real-time hazard assessment. The geographical isolation of Slettnes created systematic logistical constraints for rescue operations that amplified emergency situation consequences. The nearest rescue resources operated from bases hundreds of kilometers distant, while Arctic weather conditions frequently prevented aircraft operations and limited surface vessel rescue capability. These geographical constraints meant that rescue operations often required extended duration in deteriorating environmental conditions, increasing exposure to systematic navigation hazards. Multi-vessel rescue scenarios created additional systematic coordination challenges that lighthouse navigation frameworks could not accommodate. When multiple vessels required rescue assistance simultaneously, coordination systems optimized for lighthouse-assisted navigation proved inadequate for managing complex, multi-vessel operations in dynamic environmental conditions. Rescue coordination centers lacked systematic capability for environmental hazard assessment across multiple geographical areas while managing multiple emergency responses. Rescue vessel crew training reflected the same systematic limitations that affected commercial vessel navigation. Rescue personnel received extensive training in lighthouse navigation procedures and standard rescue techniques while lacking specialized preparation for Arctic environmental assessment and ice navigation. Rescue crews approached Arctic emergency situations with sophisticated lighthouse navigation capabilities but limited environmental expertise necessary for safe Arctic rescue operations. The economic and logistical pressures affecting rescue operations created additional systematic constraints that amplified emergency consequences. Rescue operation costs increased dramatically with operation duration and environmental difficulty, creating systematic pressure for rapid rescue attempts that might not allow adequate time for environmental assessment. These economic pressures systematically discouraged the conservative rescue approaches that Arctic conditions required for safe operations. Insurance and liability frameworks governing rescue operations reflected similar systematic biases toward technological navigation solutions. Rescue operation insurance and legal requirements emphasize compliance with established lighthouse navigation procedures while providing limited recognition of environmental assessment capabilities that might improve rescue safety in Arctic conditions. Rescue operations faced systematic legal and financial incentives to follow lighthouse navigation protocols, even when environmental conditions made such protocols systematically dangerous. Secondary vessel groundings and ice entrapments during rescue operations created cascading emergency scenarios that overwhelmed rescue system capability. Single-vessel emergencies frequently generated multiple additional emergencies as rescue vessels encountered the same systematic navigation hazards, using the same lighthouse navigation techniques. These cascading failures created emergency situations that exceeded rescue system capacity and created systematic resource allocation problems. The documentation of rescue operation failures around Slettnes revealed systematic patterns where rescue attempts amplified rather than resolved emergency situations. rescue vessels following lighthouse navigation guidance encountered ice entrapment, grounding incidents, and navigation hazard exposure that created additional emergency scenarios requiring further rescue resources. These secondary emergencies often proved more serious than original incidents due to rescue vessel resource constraints and environmental condition deterioration during rescue attempts. Weather forecasting systems available for rescue operation planning proved systematically inadequate for Arctic emergency response requirements. Standard meteorological forecasting emphasized atmospheric conditions suitable for lighthouse navigation assessment while providing minimal capability for predicting ice formation acceleration, current pattern changes, or environmental deterioration rates that affected rescue operation safety. Rescue operations received weather information confirming lighthouse navigation feasibility while lacking systematic environmental hazard forecasting. Rescue equipment deployment in ice-affected waters created additional systematic operational constraints that lighthouse navigation planning could not accommodate. Standard rescue equipment designed for open water operations required modification or replacement for ice navigation conditions, while rescue vessels lacked systematic capability for equipment reconfiguration during emergency response operations. Rescue attempts discovered equipment limitations only after committing to rescue approaches that could not be safely abandoned. The interaction between rescue vessel design characteristics and Arctic environmental conditions created systematic operational limitations that amplified emergency consequences. Rescue vessels optimized for temperate water performance possessed hull configurations, propulsion systems, and maneuverability characteristics that proved inadequate for ice navigation and Arctic rescue operations. These design limitations became critical during rescue operations where vessel capability limitations prevented effective emergency response. Communication between rescue vessels and emergency vessels during Arctic rescue operations proved systematically inadequate for coordinating complex rescue maneuvers in dynamic environmental conditions. Radio communication systems designed for lighthouse-assisted navigation provided adequate capability for position reporting and basic coordination while lacking capacity for real-time environmental hazard communication necessary for safe rescue operations in changing ice and current conditions. The systematic nature of rescue operation failures around Slettnes reflected fundamental incompatibilities between rescue system design assumptions and Arctic environmental realities rather than exceptional circumstances or operational errors. Rescue systems optimized for lighthouse-assisted navigation in stable environmental conditions proved systematically inadequate for Arctic emergency response, where environmental conditions continued to evolve during rescue operations. International coordination requirements for Arctic rescue operations created additional systematic complications that lighthouse navigation frameworks could not accommodate. Rescue operations near international boundaries required coordination between multiple national rescue systems with different equipment, training, and procedural standards. These coordination requirements proved systematically incompatible with the rapid environmental assessment and response capability necessary for Arctic rescue operations. Resource allocation decisions during multi-emergency scenarios created systematic conflicts between rescue operation effectiveness and lighthouse navigation assumptions. Rescue coordination centers faced systematic choices between concentrating resources for individual rescue operations versus distributing resources across multiple emergency situations, while lacking environmental assessment capability necessary for evaluating relative emergency urgency in dynamic Arctic conditions. The documentation of cascading rescue failures revealed systematic amplification effects, where individual rescue operations created additional emergencies that exceeded total rescue system capacity. Single vessel emergencies generated multiple additional emergencies through rescue operation failures, creating systematic resource allocation problems that prevented effective emergency response and amplified overall emergency consequences. These systematic rescue operation failures demonstrated that lighthouse navigation limitations extended beyond initial navigation problems to encompass emergency response system inadequacy in Arctic conditions. The same technological over-reliance and environmental assessment limitations that created initial navigation failures systematically compromised rescue operation effectiveness, creating secondary crisis scenarios that often proved more dangerous than original emergencies. The systematic investigation of lighthouse navigation failures around Slettnes ultimately revealed evidence that contradicted fundamental assumptions underlying traditional maritime navigation philosophy, while demonstrating the necessity for navigation system redesign specifically adapted to Arctic environmental conditions. Post-incident forensic analysis documented consistent patterns across multiple seasons, weather conditions, and vessel types that established lighthouse navigation inadequacy as a systematic rather than exceptional problem requiring fundamental technological and procedural solutions. Comprehensive incident documentation spanning multiple years revealed systematic temporal patterns in lighthouse navigation failures that correlated with predictable environmental cycles rather than random or exceptional circumstances. Investigation records showed navigation incidents clustered during specific seasonal periods when atmospheric conditions enhanced lighthouse signal clarity while simultaneously accelerating ice formation and environmental hazard development. These temporal patterns demonstrated that lighthouse navigation failures resulted from systematic environmental incompatibilities, rather than operational errors or equipment malfunctions. Physical evidence examination from vessel groundings and ice entrapment incidents provided definitive confirmation of the systematic nature of navigation hazards that lighthouse guidance could not detect or communicate. Hull damage patterns showed consistent characteristics indicating ice contact during approach phases when lighthouse signals remained fully functional and navigation calculations appeared accurate. Vessel position documentation at the time of grounding incidents consistently showed positions within normal lighthouse navigation parameters, while environmental conditions had created systematic navigation traps. Ice formation analysis conducted during multiple seasonal cycles documented the systematic relationship between optimal lighthouse, visibility conditions, and maximum navigation hazard development rates. Detailed measurements of ice formation timing, thickness development, and geographical distribution patterns confirmed that atmospheric conditions providing excellent lighthouse signal transmission systematically accelerated ice formation processes in navigation approach corridors. This evidence established definitive confirmation that lighthouse signal clarity often coincided with maximum navigation danger rather than maximum navigation safety. Current pattern measurement and analysis revealed systematic variations in navigation channel configuration that occurred on timescales incompatible with lighthouse navigation planning assumptions. Detailed oceanographic measurements documented current velocity changes, tidal circulation variations, and ice transport patterns that systematically altered navigation corridor safety within hours, while lighthouse navigation procedures assumed environmental stability over periods of days or weeks. These measurements provided quantitative evidence of fundamental temporal incompatibilities between lighthouse navigation capabilities and Arctic environmental change rates. Atmospheric optical analysis documented systematic distortion effects during temperature inversion conditions that created position calculation errors sufficient to place vessels in navigation hazard zones, while lighthouse signals appeared to provide accurate navigation guidance. Detailed atmospheric physics measurements confirmed that temperature inversion layers enhanced lighthouse signal visibility while simultaneously creating optical refraction effects that displaced apparent lighthouse position by distances exceeding safe navigation margins. This evidence established definitive confirmation that enhanced lighthouse signal quality often indicated decreased rather than increased navigation accuracy. Investigation of rescue operation failures provided additional systematic evidence of lighthouse navigation inadequacy, extending beyond initial navigation problems to encompass emergency response system limitations. Documentation of secondary incidents during rescue operations showed consistent patterns where rescue vessels, following lighthouse navigation procedures, encountered identical systematic hazards, creating cascading emergency scenarios that overwhelmed rescue system capacity. These secondary incident patterns provided evidence that lighthouse navigation limitations affected entire maritime safety systems rather than individual vessel operations. Communication system analysis revealed systematic inadequacy of lighthouse-based information systems for Arctic navigation safety requirements. Detailed examination of communication logs during incident periods showed consistent patterns where available communication systems provided adequate capability for lighthouse signal status reporting, while proving systematically inadequate for environmental hazard assessment and real-time navigation safety information transmission. This evidence demonstrated communication limitations amplified lighthouse navigation system inadequacy by preventing environmental hazard information sharing. Long-term environmental monitoring around Slettnes provided systematic evidence of environmental variability patterns that exceeded lighthouse navigation system adaptive capability. Multi-year environmental datasets documented ice formation patterns, current variations, and atmospheric condition cycles that created systematic navigation hazards on multiple temporal scales from hours to seasonal cycles. This evidence established that lighthouse navigation system limitations reflected fundamental incompatibilities with Arctic environmental characteristics rather than exceptional or unpredictable conditions. Vessel design analysis revealed systematic inadequacy of temperate water navigation equipment for Arctic environmental conditions, amplifying lighthouse navigation system limitations through equipment performance degradation during Arctic operations. Detailed examination of vessel systems during Arctic navigation showed consistent patterns of navigation equipment performance reduction, communication system interference, and mechanical system operational constraints that systematically degraded navigation capability precisely when Arctic conditions required maximum navigational precision. The institutional response to documented lighthouse navigation failures demonstrated systematic recognition that technological navigation improvements alone could not resolve fundamental incompatibilities between lighthouse navigation philosophy and Arctic environmental requirements. Maritime regulatory authorities implemented navigation system modifications that acknowledged lighthouse navigation inadequacy, while developing alternative navigation frameworks specifically designed for environmental unpredictability rather than technological consistency. New navigation protocols developed after systematic incident analysis emphasized environmental assessment capabilities rather than lighthouse signal reliability as primary navigation safety criteria. These protocols reflected institutional recognition that Arctic navigation safety required dynamic environmental hazard assessment capabilities that lighthouse technology could not provide. The development of alternative navigation frameworks demonstrated systematic acknowledgement that lighthouse navigation philosophy proved fundamentally inadequate for Arctic conditions. Training curriculum modifications implemented following incident investigation reflected systematic institutional recognition that mariner preparation required environmental assessment capabilities rather than lighthouse navigation technique refinement. New training programs emphasized ice formation recognition, current pattern assessment, and environmental change rate evaluation while reducing emphasis on lighthouse signal interpretation and position calculation techniques. These curriculum changes demonstrated institutional acknowledgement that lighthouse navigation training had systematically underprepared mariners for Arctic navigation requirements. Equipment development initiatives following incident analysis focused on environmental assessment technologies rather than lighthouse navigation capability enhancement. New navigation equipment development emphasized ice detection systems, current measurement capabilities, and environmental change monitoring rather than lighthouse signal reception improvement or position calculation refinement. This equipment development priority shift demonstrated systematic recognition that lighthouse navigation technology required replacement rather than improvement for Arctic applications. Communication system redesign following incident investigation emphasized environmental hazard information transmission rather than lighthouse signal status communication. New communication protocols and equipment specifications prioritized real-time environmental hazard sharing, ice formation reporting, and current pattern information transmission, while reducing emphasis on lighthouse bearing and position reporting capabilities. These communication system modifications reflected systematic acknowledgement that lighthouse-based information systems proved inadequate for Arctic navigation safety requirements. International maritime safety organizations implemented systematic policy changes that acknowledged lighthouse navigation limitations while establishing alternative navigation standards specifically designed for Arctic environmental conditions. These policy modifications reflected institutional recognition that lighthouse navigation standards developed for temperate maritime environments proved systematically inadequate for Arctic applications requiring fundamentally different navigation approaches. Insurance and liability framework modifications following incident analysis reflected systematic recognition that lighthouse navigation compliance alone could not ensure navigation safety in Arctic conditions. New insurance requirements emphasized environmental assessment capabilities, alternative navigation system availability, and Arctic-specific equipment standards while reducing reliance on lighthouse navigation procedure compliance for liability assessment. These framework modifications demonstrated institutional acknowledgement that lighthouse navigation standards provided inadequate safety criteria for Arctic operations. Economic analysis of incident consequences revealed systematic cost patterns that demonstrated lighthouse navigation failures created economic impacts, far exceeding the costs of alternative navigation system development and implementation. Comprehensive economic assessment including rescue operation costs, vessel loss values, cargo damage expenses, and liability settlements showed that lighthouse navigation system inadequacy created systematic economic inefficiency through predictable failure patterns. This economic analysis provided additional institutional justification for navigation system redesign rather than lighthouse navigation system improvement. Environmental impact assessment of incident patterns revealed systematic ecological consequences of lighthouse navigation failures that created additional institutional pressure for navigation system redesign. Documentation of fuel spills, vessel debris accumulation, and rescue operation environmental disturbance showed consistent ecological impact patterns resulting from lighthouse navigation inadequacy. These environmental consequences provided additional evidence that lighthouse navigation failures created systematic rather than exceptional problems requiring fundamental solutions. Technological development following incident investigation produced navigation systems specifically designed for Arctic environmental conditions that abandoned lighthouse navigation principles in favor of dynamic environmental assessment capabilities. These new navigation technologies emphasized real-time ice detection, current pattern monitoring, and environmental change rate assessment, rather than fixed position reference and signal reliability. The development of alternative navigation technologies demonstrated systematic recognition that lighthouse navigation philosophy could not be adapted for Arctic requirements. Regulatory framework development following systematic incident analysis established Arctic navigation standards that explicitly acknowledged lighthouse navigation inadequacy while requiring alternative navigation capabilities for Arctic operations. New regulations mandated environmental assessment equipment, alternative navigation systems, and Arctic-specific training requirements while reducing reliance on lighthouse navigation compliance for safety certification. These regulatory changes reflected systematic institutional recognition that lighthouse navigation standards proved fundamentally inadequate for Arctic conditions. International cooperation initiatives developed following incident investigation emphasized information sharing about Arctic environmental conditions rather than lighthouse navigation standardization. New international agreements prioritized environmental hazard data sharing, ice formation reporting systems, and current pattern information exchange, while reducing emphasis on lighthouse navigation procedure harmonization. These cooperation framework modifications demonstrated systematic acknowledgement that lighthouse navigation standardization could not resolve Arctic navigation safety problems. The systematic pattern of institutional changes following incident investigation revealed comprehensive recognition that lighthouse navigation failures around Slettnes reflected fundamental technological and philosophical inadequacies rather than operational or procedural problems requiring minor modifications. Maritime institutions systematically acknowledged that lighthouse navigation principles developed for temperate water conditions proved fundamentally incompatible with Arctic environmental requirements, necessitating complete navigation system redesign rather than lighthouse technology improvement. Long-term monitoring of navigation safety improvements